All right, welcome back. So our next set of reactions is our last one for the organic unit, is something on polymerization. So of course, polymerization is going to be the main thing that plastics are formed from. Now, they are made of stuff called polymers. So a polymer is just a large molecule made by linking together many smaller molecules called monomers. So our next definition is a monomer. Just remember, mono always means one, poly always means many. So a monomer is a small molecule, we call this the base unit, that links with many other similar molecules in addition or condensation reactions. So there's two different types we're going to be looking at. In polymerization, this is just the reaction that forms them. So this is an example of what a polymer would look like. So we notice like the little dots right here. So this just means that this continues going on, and same thing on the other side right here. It's just this whole thing just repeats. So with polymers, there's most of the ones, these are synthetic. We will look at natural ones as well, but synthetic polymers is stuff man-made, so like all plastics, nylons, PVC, Teflon, polyester, stuff like that. Natural polymers, when you look at rubber, cotton, wool, silk, proteins, carbohydrates, DNA, like all these here, is if they're naturally occurring in either in nature or plants or animals, they're the natural polymers. Everything else is man-made. Now, when we do make polymers, there's two different types of things that we're trying to accomplish. So one of the things that we have something is called structural analogs. So this is where if you can isolate a polymer and realize, how useful it is, you can try to create something that looks similar to it. So that's the similar chemical structure of a naturally occurring one. So for example, like a general protein will look something like this. We can tell we have that C double bond O. We have a bunch of carbon groups. And of course we see these bonds here, like the NH bonds here. Now when we look at nylon 66, which obviously is synthetic, we'll notice it's very similar. We have our carbon double bond oxygen. We have our nitrogens here. Now we're missing the R groups, but that's fine. But we notice how they do look very similarly. And we know proteins, well, what they do for our body, we need them to survive. Nylon, it's enclosed. So there's structural analogs where they look similar to each other, but functionally they're completely different. Now the other types of polymers that you can get is something called a functional analog. So this is a synthetic compound that performs the same function as a natural occurring one, but obviously they're not the same at all. So for example here, these aren't polymers, but this kind of give you an idea of artificial sweeteners. So we have three different artificial sweeteners right here, and we can tell that they're all very different compared to what's in them. Like two of them had these sulfur compounds, whereas the aspartame does not. We see carboxylic acid right here, no carboxylic acids in any of the other ones. We see an ester group, we see benzene. So like there's a bunch of different functional groups in all of them. So these are all functional analogs of what sugar would be. Now, if you're curious of what sugar looks like, just flick to the cover page of your organic notes. And this is what sucrose looks like. So we can tell even looking at this molecule right here, right? So this is just on literally the cover page of your notes, where we have our sucrose, and we can tell those artificial sweeteners look nothing like our normal sucrose molecule. But they do have the exact same function. That means they sweeten things, although they're all completely different. So when we get to actually naming of the polymer, it's actually not too bad. As long as you know the monomer name, all you need to do is just stick poly in front of it. So for example, if your monomer is ethene and you form a polymer out of it, you then create polyethene. So many polymers are named classically instead of in the IUPAC nomenclature, and that just means that the classical naming is kind of like the acids and stuff like that, is just names that scientists have came up with. So for example, like normally we would call this one right here phenylethene, but its common name is styrene. So if we do an addition polymerization on this right here, we get something called polystyrene. So notice how we have our repeating unit of we have two carbons with a phenyl group attached on it, so two carbons with a phenyl. And we know it's an addition reaction as well because we did start with a double bond, but now we can tell it's all single bonds going throughout because we lost the double bond and we created new bonds. So our addition polymerization, this is a reaction involving unsaturated monomer units, so basically a double bond or a triple bond. We're just going to be dealing with the double bonded units. And of course, with this one right here, we involve the double bond and they join together, involving addition reactions. So just like we had addition reactions before, we're not going to produce anything else, as we're just kind of adding two things together. So the example is very similar to what we have up here. Is if we have two ethene molecules coming together. Now, because in polymerization we need a lot of molecules, you're going to notice this N show up in front of a lot of the reactions. So N just equals many units coming together. So if we have this ethene addition reaction, so just remember for addition reactions that when two molecules come together, we break the double bonds. Right? So of course, if this happened, where if we broke our double bonds, what we would end up getting is our two ethene molecules. Of course, they're minus their double bond. But we'll notice, like, so we'll just focus on the two right here in the middle, is that we can tell that they both have 1, 2, 3, 1, 2, 3 bonds around them. So you need to have a bond. So this is when they're actually going to create a carbon-to-carbon bond just like this. Right in the middle. Now, as for the N carbons, they are also going to create carbon-carbon double bonds as well. But we're not going to keep drawing units. So what we're going to do is basically do a square bracket like this. So this is kind of indicating that this reaction is going on. And saying that at the other end, we're going to close off with a square bracket and write a little and down at the bottom, saying that this is going to repeat over and over and over and over again. And this is how we get our addition polymerization coming together. Now, sometimes, especially at this one right here, where it's the same unit, we'll notice it's a little redundant saying N-ethene plus N-ethene. So we can simplify this as well. And that's on the next page right here, where it says reaction can be summarized if we just go N, and then we go C, CH4, arrow, square, brackets, and then we write in our, which once was ethene. Now the double bond's gone, but we do have our repeating units going through like this. So what we call right here, this is just one unit because it repeats over and over again. So basically your repeating unit is how many times you draw the monomer again. So what we have right here is we have a bunch of different polymers. And we're just going to look at how to draw the polymer with the repeating unit, and then of course we'll look at some of the uses as well. And what I just drew out there was polyethylene. So of course polyethylene, or polyethylene as sometimes it's called. It's plastic insulator for wires, plastic in milk bottles, refrigerator, dishes, everything like that. So it is one of those plastic things that have many uses. So the other polymers we're going to look at is polypropylene, polyvinyl chloride, or PVC, polystyrene, or styrofoam, and of course Teflon. So I'm just going to do the first one with you, and then I'll hopefully pause the video and then try to draw the three repeating units. But for the three repeating units, basically right here, so this is just the monomer. And of course, if we're going to draw the three repeating units, we're going to have to draw the monomer 3 times. So if this undergoes an addition polymerization, right, we're going to start with, we have this, so our monomer, so we got CH2. Then remember we lose the double bond, so I'm just going to draw a single bond here, and then we got CH3 and then H. So this is one unit. So we're going to draw this repeating 3 times, so then we just repeat. So we got CH2, C with the methyl group up here, and then H. So that's 2 units. And then our third repeating unit looks like that. Alright, so this is how we have 1 unit, 2 unit, and 3 units. So obviously, I don't have enough space right here, but I'm just going to highlight our repeat unit. That's our repeat unit right here, so you can kind of put that in the square or in this one right here, but I'll kind of erase this now in a second and put that in so you can see it. But anyway, some of the uses that we have right here, you can always Google them, but we have rope and carpet is its two main uses. So I will fill in the uses there for you, but for PVC, styrofoam, and Teflon, I'd like you to try to get to 3 repeating units for the other ones there as well. All right, so pause the video, try them out, and the answer is going to go up in 3 seconds. All right, and of course all the polymers will look something like this. So we have our 3 repeating units here. We have what our repeat unit looks like, and of course some of the uses. So PVC, or polyvinyl chloride, uses insulations used in pipes, used to coat things. We have polystyrene, or styrofoam. That's of course obviously used in cups and insulation, and even some containers are made from that. And then of course our Teflon will look something like this, and that's basically used for non-stick stuff. And that's kind of how we do our addition reactions. Just have to make sure that you break the multiple bond and then join all the monomers together. So our condensation polymerizations are a little different. So it gets its name because we condense out or remove a small molecule. Now, the ones that we're going to remove mostly is going to be H2O. You can remove ammonia and H3 or even HCl, so different functional groups depending on what we have. But we've already seen a condensation reaction before, which is our esterification, because when they came together, we produced water. So that's why I think if you look back through the notes, it said esterification is sometimes called a polymerization reaction. A condensation reaction, not polymerization. Sorry. So if we just look at the next page here, we'll see an example of what a polymer will look like under condensation reactions. And we will notice that we can see our ester functional group. Here, but then also here is where as well, sorry. So this tells us that, of course, we needed to link them together. Where you had, obviously, right here, this is our carboxylic acid, and on the end right here must have been an alcohol. So to form this ester linkage. So, of course, how this is going to look is that, with bigger examples, you have to make sure that if you see something like a carboxylic acid, where if we get any number of some sort of carboxylic acid, right? So you will notice that we need to have two functional groups kind of come together. Now we can have the same repeating unit, or we can have something different as well, like some sort of diol. So you'll notice 2 carboxylic acids and 2 things together. Now, two carboxylic acid functional groups? So we need that because we're going to have these right here are going to come together, right, and condense out our water. But we needed the alcohol group over here because it needs to react with then the end of a carboxylic acid, so we can kind of keep this condensation reaction going. Because if it was only one carboxylic acid and one hydroxyl group, then we're only just going to form an ester. So you have 2 of them coming together. Now, of course, when these come together is when we are forming our thing. I'm just going to have to draw it down here because I don't really have enough space up above. Right, we're going to have square brackets. Now, obviously over here we're not going to draw our carboxylic acid, so we need to lose the H, but we're going to have our our oxygen, and then we are going to form our first molecule together. Right, so that's that. Now we have our ester, which is just 1 carbon, 2 carbons long, and then finally our oxygen is going to be bonded. Sorry, we don't need to put in the oxygen there because we have an oxygen over on the other side. And our bond going like this. Right, so we got 1, 2 carbons here, and that's just showing the bond. And of course, we repeat. So this is just one repeating unit of how it'll look like, but we notice we do have the combination of our first and our second one right here. And we do see our ester linkage right here. And of course we know that this is going to form an ester right here, right? And of course we even have another ester linkage in here. So we can tell that this is coming from a condensation one. Now, if we have something that's not an ester, but let's say a bigger one, or ammonia comes into play, this is when we get something called an amide or a peptide linkage. So this is when we condense out water still, but we end up getting this functional group with our nitrogen, but we're still going to react with a carboxylic acid. So kind of what happens, like this amino group is what's called with the nitrogen, it's still going to react. Now here we're going to have the hydrogen, so one of the hydrogens from our amino group and the complete hydroxyl group, or the hydroxyl group from our carboxylic acid, is going to come together, and of course that's where we get our boom, amide or peptide bond, and this is actually how nylon is formed. So we have two of these things right here coming together. Now, for the most part with these types of reactions, it's mostly just recognizing what is going on. So any of these reactions, like you could have that, or they could look completely different. So this is kind of the example that we can have right here. So as long as you just recognize that if you do have something that looks odd, that's fine. Just so you know, if we are asking for some sort of reaction, so in this one right here, I'm not going to draw out the reaction again. We could just be given something like this, where we have this molecule, we can tell we have our carboxylic acid on one end, and we have our amino functional group on the other end. This could undergo a condensation reaction, basically react with itself, where we're going to get oxygen bonded to the carbons, something like this, our nitrogen, and then something like that, right, where we still see, you can imagine that this oxygen, or sorry, that oxygen can't be written in here because that oxygen needs to go for the amide linkage. So just straight line over here, right, because remember, this hydroxyl functional group, and these here are going to form to make our water. So sorry about that, so just go back and rechange that, and this is what the ester will look like. Or sorry, not the ester, the polymer will look like. Now for the most part, like I said, with a lot of these here, it's mostly just picking out what type of linkage it is, or recognizing what type of reaction is going to be, so whether it's an addition, polymerization, or condensation one. And this is just an old diploma example right here, where you have this particular molecule, so polyethylene, whatever that is, terephthalate, commonly abbreviated PET, is used to make polyester textiles. Anyway, so we have all that. So basically we have our monomer right here, actually two monomers. We have our polymer right here, and this question is asking, so in the polymerization reaction above can be classified as blank, and the inorganic product is blank. So of course, when we recognize, we see a carboxylic acid functional group right here, we see an alcohol functional group right here, so we know this is going to be a condensation reaction, so it can't be C or D. And then of course, the inorganic product, we know from a condensation reaction, what's going to condense out? Well, it's an esterification, so we get H2O, and the answer is B. And that is it for organic chemistry. So our next lesson for this week, we're going to be looking at starting our new unit, redox, and of course next week we will have the assignment 2, and so that will focus on just the organic reactions and probably look at some sort of unit assignment as well for all this. So anyway, see you guys for the next lesson when we start electrochemistry.